This is a picture about the molding of plastic products. First shown in 1942, it has been revised to meet the changing and improved techniques of molding. The film is presented by the Boonton Molding Company, with the hope that this new edition will prove as popular as the original version. The photography is by Paul Manner. It was written by Ralph Schoolman, edited by Elmer McGovern, and narrated by me. It was produced by Max Lasky Film Productions. We have entitled it, The Shaping of Things to Come. You know what molding is. You did it way back in your childhood days, when you filled a form with moist sand. And there, wonderful sight, a molded valentine. Then maybe you tried it with dry sand and came up with only a mound of sand with no shape to it at all. Don't mind, fella. We've had our problems too. But out of them, we've learned that some things mold, some don't. Uh-oh, here's another youngster due for a disappointment if she's expecting to mold the shape of that picture. It's no use, little girl. It won't work. But at least you've discovered that the way your mold is shaped plays a big part, too. Remember when you watched with hungry eyes as Mother turned a golden sunshine cake out of its mold? A thing of beauty. Then, when your new bride tried the same thing, same recipe, you found that conditions of baking or molding had to be just right, too. Well, anyway, molding plastics has the same problems and a great many more. Here, for example, are plastic products which, except for color, may look as if they've all been made from the same kind of material. Actually, each one is different. They have just one thing in common. All are made of thermosetting plastic materials. Such plastics, when subjected to heat, first soften, then cure and harden permanently. But there are three kinds of thermosetting plastics in commercial use, and each has different properties: phenolic, melamine, and urea. And these, as they come to the molder, have been combined with any one of a score of different fillers for different uses. Here, the resin is phenylformaldehyde, the filler, wood flour. Canvas with a phenolic resin, to take really bruising wear. Asbestos with phenolic, for heat resistance. Other fillers are cotton flock, graphite, short lengths of fish line, anything that best suits the purpose. Here is urea formaldehyde, combined with cellulose, where pastel colors are wanted. And here is shirt material, shredded and combined with melamine, where light color and shock resistance must go together. For other uses, other fillers. We carry over 500,000 pounds of these materials in stock at all times and feed them through 130 presses at the rate of 200,000 to 300,000 pounds a month. The molding of the very first Bakelite products started here in this little town of Boonton back in 1908. So a great deal of plastics activity has grown up here through the years, and many compound makers are within easy trucking distance of this plant. Each drum contains a definite material: phenolic, melamine, acetate, nylon, and on through the list. But the different colors and varying degrees of flow characteristics in each compound make it necessary to carry about 150 types in stock. So, there are your materials. Now you need molds to fashion these materials into 10,000 different shapes. Many of these shapes are commonplace in our everyday lives. We use them time after time without giving them a second thought. Yet, for each, there is a perfect mold, designed by an artist, blueprinted by an engineer, fashioned into steel by a master craftsman. We design the molds, but making them is a job for specialized die makers, using a lot of intricate and complicated machines. But you need more than materials and molds to make molded plastics. In molding, it's important that just the right amount of material gets into the mold. So the compound is accurately weighed out into the required units before going into the molding room. For certain jobs, the material goes through pre-forming machines. The material doesn't change character at all. It's just pressed into shape very much as you'd pack a snowball. Pre-forming makes the compound easy to handle and also provides quick, accurate weighing of small amounts. The pellets are made in various sizes and shapes, depending upon the mold in which they're to be used. Materials and molds come together in the press room, where they meet the 4 horsemen of the molding process: time, temperature, pressure, and maybe the most essential of all, care. The large presses are for semi-automatic molds. The small presses are for hand molds. Let's start molding with this simple little piece. The trick is to keep it flat to within 2/1000ths of an inch, for it has a precision job to do. The mold for this piece comes in 3 sections and turns out 7 rings in each molding cycle. A preformed pellet goes into each of the 7 individual feeder holes leading to the mold cavity. Each pellet makes a single ring, with a little to spare, as you'll see. The top section has 7 plungers. These fit the holes exactly, and when the top goes into place, the mold is ready for pressing. The platens in the press are heated by circulating steam, and in turn heat the molds to well over 300 degrees Fahrenheit. These are known as hand molds because they're assembled and separated by hand outside the press. They weigh from 18 to 100 pounds, and in actual operation remain pretty close to press temperature. Heat for the presses is supplied by our power plant. 2 boilers do the job, but there's a 3rd on hand so that maintenance and repairs won't stop production. Instruments of all kinds keep that power under constant control. There's also a pump room to supply hydraulic pressure, pumps for high pressure and low pressure. Double sets here too, so if one bows out, the other goes to work. A vacuum cleaning system for the entire plant makes for cleaner working conditions and products. From these sources, pipes run all over the place, each with its special color, so you'll know which is bringing water, air, or steam to the presses. Both temperature and pressure are under careful control, and the time in the press is accurately measured. When the pressing is over, our 7 rings are joined together by a thin sheet of excess material known as flash. Later, they'll be finished as individual rings. Here we have a more difficult job, and at the same time, evidence of a happy marriage between plastics and metal. Holding the metal inserts in exact position during the curing period is a problem. It's solved here by using a transfer mold. The actual mold cavity for the piece comes in 2 halves. 2 of the springs fit into 1 half, 1 spring fits into the other half. Then the 2 halves come together, and there's the mold. But we still have to get the material into it. So the split mold goes into a holding ring, and a transfer pot is fitted over it. There are small channels in the pot chamber that lead down to the mold itself. The powder is poured in. The top of the transfer pot has a plunger that fits the chamber exactly, and that's the way it goes into the press. A bit of animation will show how the material flows in a typical transfer mold. The powdered material goes into the upper chamber. Heat softens it to a honey-like consistency, and the plunger forces it down the channels into the mold below. This type of molding has many applications and solves some difficult problems. In this case, to hold the inserts against the movement of the molding compound. Taking the mold apart is sometimes more of a problem than putting it together. Quite often you'll find that the real ingenuity of mold design comes in getting the piece out after it's molded. In a few instances, we've changed actual production procedure so that you can see what's going on, but there's no royal road to mold opening. It takes time and it takes care, or you'll end up with a broken piece, or what's worse, a broken mold. Making handles for Farberware kitchen utensils gives us a different reason for using transfer molding. Now, these handles are solid, irregular in shape, and must be parted along the center line. Molding in the conventional manner would result in a heavy flash, high cost of finishing, and probably an unsightly mark along the top of the handle in spite of our best efforts. So, the logical thing to do is to clamp the mold closed and shoot the material into it. It's done in a semi-automatic transfer press. First, steel cores are inserted in the mold to provide holes in the handle for attaching to the utensil. The cores must be removed after the piece is molded. When the press is closed, the material, electronically heated preforms, are placed in the pot built into the top half of the mold. The transfer ram starts down when the safety gate closes, forcing the material into the mold. When the cure is completed, the transfer cylinder is withdrawn and the press opened. 8 complete handles that need only a minimum of finishing to become perfect complements to a fine product. Here's a piece, believe it or not, that's a windshield wiper case. For an ocean liner, of course. It has 22 brass inserts that must be embedded in the plastic at specific points. There's an added problem of depressions and undercuts. Those require a mold with many removable parts, or the piece won't come out of the mold. This is the bottom section of the mold in which the piece is made. It's a semi-automatic mold rather than a hand mold. A final difficulty, as you'll see, is presented by the molding of the post in one corner. But special problems need special handling. There are the inserts to be put in place all around the mold, and pins to hold them and small parts of the mold itself. So, it's easier to make the whole bottom section of the mold removable than to walk all around the press. When this section is fully assembled, it's lifted over to the press. The top of the mold is fastened permanently into the press, and it too has its complement of inserts and small removable mold parts. There will be 600,000 pounds of pressure on this mold, and keeping those inserts in place and intact presents a bit of a problem. Here's the brass insert that goes into the top of the post. Now the compound goes into the mold cavity. This is a canvas filler material that will make all of the piece except the post. The loose compound bulks up to 6 times its molded volume, so there's quite a lot of it to go in the space available. When the material is all in, the bottom of the mold is lifted into position. Additional preforms to complete the post are fed in at the bottom. The mold comes together and the curing goes on to completion. Getting the bottom section out of the press was no problem, as the top and bottom were pulled apart when the press opened. But now, every one of those pins that held the inserts in place has to be removed, and all the smaller mold parts taken out. It's a hot and heavy job when you consider that the operator is wrestling with about 80 pounds of steel heated to 320 degrees. Here's a molder's dream, or a molder's nightmare, depending on your point of view. This is one of the most complicated pieces ever molded. It takes a total of 22 different pieces of steel to make up the complete mold, and putting the different parts of the mold in place is a long, slow process. Still, it's a tiny fraction of the time that would be required if you tried to machine this piece out of any other material. There's only one way to make it. That's out of plastics shaped in a steel mold. Those pieces fit together within the thickness of 2 human hairs. And they can't be forced, or in no time at all you'll have a $10,000 mold ready for the scrap heap. It's after the curing cycle is completed that the fun really begins. We won't take you through the entire operation, but just give you a fast count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Anyway, at long last, there's the piece. Yep, sometimes molding really becomes complicated. For economical production and fine quality control, the molding of Boonton ware is a good example. Here is a complete modern molding operation carried on in an air-conditioned room. It starts with the preforms being electronically heated before going into the press. The operator just pushes a button and 3 sets of platens go to work at the same time. As a constant check on proper curing, charts automatically record the time and temperature. The molding compound is Melmac, perfectly suited for dinnerware. Because of its extremely high resistance to breakage, among other qualities, it withstands rough treatment, washing, chipping. In fact, we even guarantee it for 1 year in home use. Pardon the advertisement. When it comes to little fellas like bottle caps, or even larger parts, then we can really go to town in these completely automatic robots of our own design. The material is automatically taken from the drums, and the cycle begins with 96 feeder tubes releasing the raw powder into 96 tiny buckets. The cycle continues as the buckets slide over and empty the material into 96 cavities. Here it's pressed into pellets and preheated at the same time. All the while, every movement is under the watchful eye of an electrical control system that is its only operator. The wafer-like preforms are pushed up through the holes in the tray that carries them to the curing molds for final shaping. In just 40 seconds, the press opens, and here at the front, we can see another tray sliding into position to receive the finished caps. The plastic is still soft enough so that the stripping action does not injure the threads. The caps slide into a tumbler that removes all the flash, and the job is done. 96 finished bottle caps in less than a minute's time. The caps now go through another machine that turns them all face up, cuts paper liners from a long strip of treated paperboard, and inserts a liner into each cap. From here, they go to the inspection department, where every cap must pass a top and bottom scrutiny before a row of eagle-eyed inspectors, even if it's only to prove that the world still can't get along without the human touch. There's another group of molding materials that soften when heated, harden when cooled. These are called thermoplastic. Polystyrene, fast molding, colorful, transparent if you want it. This is the material that floods the stores with all sorts of housewares and toys. Acrylics for transparency, toughness, and optical qualities. Polyethylene, made from ethylene gas, produces such things as flexible bottles and ice cube trays. And this material you know well as glamorous stockings, for this is nylon. But it also molds in tough, thin sections, and so has a number of important jobs to do in industry. Then there's cellulose acetate for toughness, resilience, and high polish. Thermoplastic materials call for a different type of molding, injection molding. A large range of different products are turned out in these machines, singly or in multiple units, which are joined together by a sprue. The sprues are removed here, and then the pieces are ready for finishing and inspection. In this type of molding, quite a bit of finishing is done right here, and the material that's snipped off goes right back into the machine, because thermoplastic materials will again become soft when reheated. First, all moisture must be removed from the material. That's done either in wall-type drying ovens or in drying units attached to the hopper of the press. And here's what happens inside the machine. During actual operation, the heating chamber remains filled with a material which is softened by the heat. The plunger at the back picks up a definite amount of the material released from the hopper and forces it into the chamber. At the same time, it exerts a pressure which forces the soft material through the nozzle into the mold. Pressures range up to 20,000 pounds per square inch. When the plunger retracts, the pressure is released and the mold opens. This machine is molding bird baths, a top and bottom every 25 seconds. This rapid cycle is possible because the mold is kept cool by circulating water, so the hardening takes place almost at once. Cementing the two halves together for a leak-proof joint is easily accomplished with an acetone gun, right at the press. These threaded liners for electrical insulators are an example of some of the unusual possibilities of injection molding. They're made this way in clusters of 4. To remove the piece from the mold without distortion, the mold must be unscrewed, not the piece. It's done by a set of gears that rotate the inside threaded cores as the press opens. Here's a view from underneath, and here's the same view with the camera action slowed down so you can see the operation in more detail. And now, just in case you are enjoying the pleasant myth about plastic products popping out of their molds all finished and ready to go to work, let's go upstairs and watch some pieces go through their finishing and inspection routines. Every single part that is molded goes through a preliminary inspection. This is not a spot or percentage inspection. It goes over every piece, whether large as a tabletop or small as a dime. In all, there are 16 possible causes for rejection at this point, but the inspector knows just where each piece is likely to go bad. Even so, he's better off than the molding foreman. There's an average of 8 possible causes for each of the 16 defects. The first job after inspection is to have rough edges smoothed down. The flash or overflow must be removed. Here, the good old-fashioned hand filing will probably be with us always. Small lots, odd shapes, interfering inserts, all limit the possibility of automatic machine finishing. Pieces that are difficult to hold can generally be fitted up with a wooden form that helps the operation along. Scraping and cutting, too, will likely continue to be a part of finishing. Scratching out bits of flash that can't easily be reached in any other way. Punch presses fitted with special dies do a number of trimming jobs. These canvas parts that are made in multiple molds would be hard to trim by hand because the flash between the pieces is just about as strong as the canvas itself. Lathes do a host of precision jobs. Here, a commutator ring has its center diameter finished to a tolerance of 0.5 of an inch. It's first drilled, then bored to exact size by a fine diamond tool. A plug gauge checks it to within 1/5 of the thickness of a human hair. Some lathe jobs are merely to remove the flash from circular edges. Even tiny objects like this get the same type of precision handling. And here's a set of special grinding machines of our own design. They perform a number of unusual operations. They work on odd shapes, They grind just parts of a circle and skip other parts. Not a bad trick at that. There are batteries of drills that ream holes and bore holes, singly or in multiple units. Here, 10 holes are being bored at the same time. For the most part, these are not actually drilling operations, they're flashing operations. The excess material is being removed from holes that can't be molded all the way through. And finally, there are the varied hand finishing operations on scores of different parts. Tens, hundreds, thousands of each part. Every single piece individually handled and carefully turned out to be sure it's ready to do its job. Then there's buffing and polishing to do if you want a really deep finish, though many pieces are quite satisfactory with the surface finish they get in the mold. And at the end, every precision piece is individually checked. We have to be sure that flat surfaces are really flat, that precision threads fit the go end of a go-no-go gauge and don't fit the no-go end, that all electrical contacts are secure and dependable, that round pieces meet their tolerance limits at every point of the circle. Remember those little rings? They're checked here for flatness on a shadow graph. The shadow is enlarged 40 times and must stay within tolerance limits while the piece is being revolved. A microphone mouthpiece must have a definite thickness and a definite outside diameter. 4 prongs must not only be the same length, they must be an exact length. 3 indented corners must check to a hair's breadth. Simple pieces or complicated pieces, all must take every test and meet it. Remember that plastics are not of themselves precision materials. It takes skilled molding and painstaking finishing to get precision results. Every day, thousands of molded parts are on their way to go to work somewhere, to do a job better in many cases than it could possibly be done by any other material, and in some cases, to do a job that was considered impossible until the advent of plastics. But the value of any product must be measured by what it means to the welfare of people. That's one thing we here in Boonton always keep in mind. So, when you examine these many different products and find our name on them, you'll know that we're always trying to keep that a proud name in the shaping of things to come.